Well, good to see you back after yesterday. I did notice only about 9 people are signed up for Mastering Chemistry so far. I know we just had 1 class, but please do that because, like I said, the first assignment's due this week. Though, if you need more time, just tell me. I can always extend those dates. The way Mastering Chemistry works, if you haven't done it before, you work through the problems. At the when it's past the deadline, it won't give you credit for what you do anymore, but if you still do it, it'll save all your work. And then if you come say, hey, I didn't get that done by the deadline, can you set it back? I could say, yeah, I'll set it back. And then it'll give you all that credit that you did. So like if it's due at midnight or something, and you're still working on it until 1 in the morning, keep working on it. And then just tell me that you did that afterwards and I'll reset the date. Those deadlines are mostly to keep you on track. I don't really care if you stick to them or not. I'll push the deadlines back if you need them on the homework. But I would encourage you to stick to the deadlines because that'll be like what we do in class. I also got the question to please talk about what topics we're doing in order for those of you who are using different kinds of books. So I will post an updated schedule that doesn't just say chapters, but has chapters and topics. So if you're using different books, you can follow along. So today is going to be, we're going to talk about different ways of classifying matter. We're going to talk about temperature and other types of units and unit conversions. Then we'll take a little break. We'll come back and talk about atoms and atomic theory. So, sound good? All right. Also, at the break, or maybe a little bit before, I'll have a handout with some practice problems, and we'll spend some time doing that. Thursday as well, kind of to wrap up the week, I always like to have a lot of practice with the problems because like we talked about yesterday, that's what the exams are going to be. That's what most of the class is going to be. So I'll bring those in for you and we'll get to work on those a little bit too. Okay, any questions or anything you want to know before we start on this stuff today? Okay. Does this figure look new to anyone? Have you heard those terms before, solid, liquid, and gas? So that's one way to classify matter. And what are those 3 things called? If something is if you said, oh, that is a gas or that is a solid, what attribute are you talking about? It's state, right? So this is classifying by state. Okay, saying if it is a solid, a liquid, or a gas. What is the difference between a solid, a liquid, and a gas? And we can all probably look at them and know whether it's a solid, liquid, or gas. But how do you actually define that? Do we know? Or we'll just pick one of them if you know. Like what's a solid? Yeah. That's a good idea, and for a lot of materials, I'd say most materials that works, but think about something like water. Ice is actually less dense than liquid water. So that doesn't quite work out, and that's an exception. Like you're right for most materials, but it's not universal. Is there a universal definition that we can go with? Yeah.
Is it about like the shape and volume?
Yeah, what about the shape of volume, specifically for a solid?
Would be definite.
It'd be what?
Would be definite.
Right, so what we would say here is a solid has a defined, or let's say definite. Definite shape and volume. I realize that kind of looks like a Z now. Fix that. Definite shape and volume. What that means is that no matter where you put a piece of solid, it always looks the same. It always has the same shape, and it always has the same volume. It always takes up the same amount of space. This figure shows them in these flasks because that's like putting them in a different container. So how does a liquid differ from a solid when you put it in a container?
It has the same volume, but it takes the shape of whatever container you're putting it in.
Right. So a liquid has a definite volume, meaning that if you have 50 milliliters of a liquid, it's always 50 milliliters no matter what you put it in. or if you spill it on the floor, whatever, it's still 50 milliliters. But it takes the shape of its container. Why this isn't writing well. So definite volume, but it takes the shape of its container. Can I close some stuff up here? Need that, don't need that. Oh, there's my face. Let's try that again. Okay. And then, okay, so then how about a gas? How's a gas going to be different from that? Right. So now when we talk about a gas, you can do it. Takes shape and volume of the container. Hang on a second. Let's see if I can calibrate this thing better. Sorry, first one of the year is always interesting. These things didn't work. Okay, well, we'll figure it out. Okay, so that's a way that we can classify by state based on this idea of taking shape or volume of container or being fixed. With that gas one, it's a little bit unusual. We don't necessarily think about it, but if this is a 1,000 milliliter beaker and it's empty, it's not really empty. It's filled with 1,000 milliliters of air, right? So there's 1,000 milliliters of air in here, but if I pressurize this, there would still be 1,000 milliliters of air, but there would be more molecules in there. We'll talk about that when we get into the gas laws and stuff. But with a gas, you can't, it doesn't have a fixed volume. Its volume is whatever the container volume is. And when we talk about how pressure and things like that affect gases, we'll get into that more. But the definition is just thinking about how it's going to fill that container. All right, so that's one way of classifying matter. That's probably the easiest. You've been learning this stuff since you were in preschool and probably knew some of those terms then. What's another way to classify matter? By what?
Plasma.
Well, plasma is technically another state of matter. It's a little bit different because it has to do with how the electrons are, rather than being localized, they're delocalized. They're not attached to their nuclei. We're not really going to talk about plasmas in here, but what about besides the states of matter? What's another, if we wanted to say, like, what is the difference between this thing and this thing? Any idea what another way we could classify matter is? Or how people have done it in the past?
Or chemical characteristics.
Yeah, chemical characteristics or composition. So we can classify by state, but we can also classify by composition. What it's made out of. So the way we're going to do that is kind of like we're going to make kind of a flow chart about how we decide what something is based on its characteristic. And our first decision we're going to make is it a pure substance or is it a mixture? So our first classification is we can separate materials into pure substances and mixtures. And what would be the defining characteristic of whether we call something pure or whether we call it a mixture? How would we make that distinction?
Isn't pure substance just like not like just like one specific thing, and a mixture is two or more things?
Kind of, but it depends on how you define thing. So let me give you an example. Elements, if you have a single element, that's pretty obviously a pure substance, like you're saying, right?
Mm-hmm.
But what if you have a molecule? What if you have water? Is water a pure substance or is it a mixture? It's made up of two things if those things are atoms, but it's still water and has its own characteristics. So how do we define thing? Yeah.
It's a mixture, like one or more different.
Yeah, but so now we've got a new word. What's a compound? One or more atoms? And that's pure?
That's
Or wait, yeah. We have to settle on some terms here. So let's do it this way. Let's talk about how we separate these things. So let's talk about how we separate them or how we break them down. What might be the difference in how you can separate a pure substance, or how you could break down a pure substance versus how you could break down a mixture? That might clarify this. Which one do you think is maybe easier to separate?
mixture.
A mixture. And what do we mean by easier? If you think about things you might do in the lab, what does it mean for something to be easier to separate?
Break apart bonds.
Yeah, that we don't break apart bonds, right? Because that would be harder if we break apart the bonds. So the way we're going to define these is that a pure substance right? Okay, I don't know what's going on with the pen here today.
You're having a hard time making these.
Yeah, it doesn't like ease, I guess. Let's see if I can unplug it and plug it back in again. Yeah, it's the ease. Let's see. Even uppercase the ease it doesn't really like. No, it doesn't like anything. So we'll say a pure substance can only be broken down by chemical reactions, meaning that we're breaking bonds. We're changing the nature of what something is. So if you take water, which is made of hydrogen and oxygen, you break it down into hydrogen and oxygen. Those are very different compounds. Those are gases, right? Hydrogen gas and oxygen gas. So you've changed the very nature of what something is, and you've had to do a chemical reaction to do that. We'll talk about this a little bit more, but what are some features of chemical changes? When something changes chemically, what do we tend to see happen in a chemical change? We'll do one a little bit later, but yeah. Color change is sometimes a good one, yep. Change of mass, how so? Okay, so it's gaining mass by reacting with something else, yeah, through oxidation, sure, that's one. What else? Temperature, yeah, if something gets cold or hot, there's a decent chance that there's a chemical process going on because you're breaking or making bonds and then energy is being released or absorbed. So those are the kinds of things that could break down a pure substance. They could break down a chemical. So then a mixture is going to be the opposite. We're going to say a mixture can be separated by physical means. To separate something by physical means that you don't change the chemical nature of anything. Everything stays intact. So what's an example of separating something by physical means? Anybody have an idea? Could be very simple.
Like this, using strainer, like.
Yeah, sure. Using a strainer. So you've got a bunch of junk floating in your, I don't know, soup that you made or something, and you pour it through a strainer. The strainer catches the solids, and the liquids go through. So that's the way that you've separated a mixture. The stuff that you've separated is still the same stuff. It's just separate now. What's another way? Yeah.
Boiling?
Boiling, sure, distillation. So if you had salt water, let's say, you could let the water evaporate. The salt would stay behind in whatever the container was, and you've then separated the water from the salt, but you haven't changed the chemical nature of anything. You still have water, you still have salt, they're just not together anymore. So that's kind of how we're going to define a pure substance versus a mixture. The pure substance can be broken down by chemical reactions, the mixture cannot. Or the mixture can be separated more easily by physical means. Distillation, filtration, chromatography is another one, if you know what that, if you know that one, that's a kind of a special chemical one. Just separating things like manually would be another one, just sorting like with your hands. All right, so let's talk about the subgroups of these two. If you know that something is a pure substance, it can be one of two things. And if you know something is a mixture, it can be one of two things. What are the two, what do you think is, well, let's say, what's one of the pure substances? What's one of the categories of pure substances? An element, yeah, that's going to be the purest of the pure. So if we have an element, what is that? How do we know we have an element, a single pure element?
It's up there.
It's up there, yeah. What are those things, like what are the defining characteristics of that? Yeah, there's only one type of thing there, of atom. So an element is made of one type of atom. So every atom in an element is the exact same type, has the same protons, neutrons, and electrons, and that makes that substance an elemental substance. So the other type of pure substance then is the other things we were talking about, the compounds. So a compound is going to be made of two or more elements chemically bound together. There's a chemical bond between two or more elements, and the only way to break them is by doing a reaction where we would see a change in temperature or a color change or those things that we talked about, some bubbling, that kind of thing. But a compound is still a pure substance, and this is probably the part that people get wrong most about this classification scheme, is that seeing multiple elements makes you think it's a mixture, but if those are chemically bound together, it's still a pure substance. It's called a compound. So water, carbon dioxide, even big stuff like a protein could be considered a pure substance, even though it's going to have thousands or millions of atoms in it. If they're all chemically bound together, that's still a single pure substance. All right, so then the mixtures, we're going to separate into two types of mixtures. The heterogeneous mixtures and the homogeneous mixtures. What do you think is the difference between those two?
Homogeneous is one like mixture. I don't know, it's like there's multiple things in the mixture.
But isn't there always multiple things in a
You can,
mixture?
like, see that.
Yeah, that's kind of the main thing, is that homogeneous mixture, we're going to say, is uniform throughout, that it's completely distributed in the mixture so that it almost looks like one thing, looks like a compound. Most homogeneous mixtures can also be called solutions. And heterogeneous, there's a couple different ways that we can say this. Let's see, how does your book say it? Just to be clear. We'll call it regional variation. Another way to say that is there's different domains. That's kind of the more materials science-y way to say it. That you can see parts in one area that are more dense in one thing than another. So for example, let's look at coffee. Everybody know what coffee is? Coffee. Okay. So where does coffee fit on the scale? Is it a pure substance or is it a mixture? It's a mixture, because what's in coffee? What are some of the pure substances that are in coffee?
Water.
Water, that's what it's mostly made of. What else?
Cocoa bean mixture.
Well, hopefully that's been filtered out. Like, what kind of molecules do you think? Just like in general. There's one that's important to most people. Caffeine would be one, right? And then you've got other things, colors, the molecules that make it look dark. You've got flavor molecules, all that stuff that comes from the beans. So that definitely makes it a mixture. Now, is it a heterogeneous mixture or is it homogeneous? Homogeneous, because you don't look at the coffee and you'd say, okay, the caffeine's over here and the water's over here and the color's down here. It's all distributed throughout. Now, if you took that same cup of coffee and you put a bunch of dirt in it, it's the new thing, it's dirt coffee. I don't know, you've seen it. You put a bunch of dirt in your coffee. Now it's a heterogeneous mixture, because there's clearly dirt and there's coffee. And you can see where the coffee is, and you can see where the dirt is. It's not uniform throughout. Okay. So let's practice classifying some of these things. Get some examples here. Let's look at our 4 categories again. And here's a few different types of substances. Helium, like in a balloon, 14 karat gold, water, cereal with milk, where would those things fit here? So where would you put helium? Element, right? It's a single pure element. He is one element. So helium in a balloon will be entirely just helium atoms. What about 14 karat gold? What is it made out of, I guess?
Gold and like nickel or something.
Yeah, 14 karat gold is an alloy, which means it's gold mixed with some other stuff. What's pure gold? Anybody know? What carat is it? 24 is pure gold, but usually that's not great for jewelry because it's really soft and it can dent and bend and it's expensive. So we alloy it with other metals and make it 14 karat, which makes it stronger. So that becomes now a mixture because it is gold, but also other types of metals. I'm not sure what's in there. Iron probably, maybe nickel. Silver, I think, is in 14 karat gold as well. So is it a heterogeneous or a homogeneous mixture? I heard homogeneous. Well, yeah. Yeah, because when you look at a 14 karat gold, like a ring or a necklace or something, you don't see the different types of metals in it. It all looks the same throughout. So that makes it homogeneous, uniform throughout. It's also known as a solid solution because it's a solution of different solids mixed together. Okay, where does water fit in here? Well, let's see. Is water something that can be separated by physical means or not? It's not. If you do something to water, you're changing it. It's no longer water. So that makes it a pure substance, and it's made of multiple elements, which means we have to put it in the compound category. And what about cereal with milk? Yeah, mixture. Heterogeneous or homogeneous? Heterogeneous. You can see the cereal, you can see the milk. The marshmallows, if you like good cereal. Did anybody have any Lucky Charms this morning? No. Sorry, maybe tomorrow morning. You should get some. So there's two ways of classifying our materials, both by state and then by composition. All right. So now let's focus again on this idea of being able to change things physically versus chemically and what we can look for in that way. So I'm going to list a couple things happening. We're going to decide if that's a physical change or a chemical change and why. So number one is going to be ice melting. Number two, sugar dissolving in water. 3, gasoline burning. And 4, salt, sodium chloride. And water. All right, so is it physical or chemical process that's happening here? First one, ice melting. Is that physical or chemical? Physical. That's right. How do you know? Yeah, how do you know that that's a physical change and not a chemical change?
Yeah, like breaking apart bonds or whatever.
Yeah, you're not changing any bonds. And one way that we can express that is through writing it kind of like a chemical reaction. So ice would be H2O solid. And when it melts, it becomes H2O liquid. But it's still H2O. So since it hasn't changed any chemical composition, we can conclude that that's a physical change. All right, what about sugar dissolving in water? We're going to call that chemical or physical? Chemical? Why chemical? Okay, anybody else want to give a shot? Yeah.
It's breaking down covalent bonds.
It's breaking down covalent bonds. So when sugar is dissolved in water, it's no longer sugar, it's something else in there.
It's not simple.
Well, now we got some disagreement. Why physical?
Because, I don't know, this is for this, I know how to answer this salt one.
Okay, we'll get to that one in a minute. Yeah,
I think it's physical because you still have sugar and water.
it's physical because it hasn't changed. Yeah, and I think that's fair. I would say that's the same thing. That this is also physical. Because again, if we write that out, glucose is C12H22, 4. If we're talking about 22 sucrose, O11. And that starts as a solid. And then when it's in solution, it's still sucrose. But now it's aqueous sucrose, so it's sucrose in solution. So again, it hasn't changed any characteristics of what it is. It's just surrounded by water molecules. We talk about solutions, we'll get a little bit more into what that might look like, but it's sugar that's surrounded by water molecules. There's a picture of this in your book, on page 11. How do I get to? Okay. Let's just grab this part. So you've got solid sugar where the molecules are all lined up there. and then it gets dispersed with water molecules in between. So that would be certainly forming a mixture, but forming a mixture is not a chemical process, that's a physical process. So, so we would call this a physical change. All right, what about gasoline burning? Chemical, why is it chemical? Well, carefully, you're creating energy, right? You're giving off heat. Yeah, you're breaking the bonds in the gasoline. That's why there's so much energy in gasoline. And what are you forming? What are you turning it into?
Water and carbon dioxide.
Water and carbon dioxide, right. So this is a chemical change. And it would look something like C8H18, which is a liquid. Oh, this thing is not happy today. It's reacting with oxygen gas to form carbon dioxide gas and water vapor. Okay. It's not balanced, but that's the basic reaction. So we're changing the nature of the gasoline. We're turning it into something else by breaking bonds and making new ones. So that's chemical. All right, and then finally, sodium chloride dissolving in water. Physical or chemical? Why physical? You said you were excited to answer this one, right?
If you evaporate the water, there's still salt.
If you evaporate the water, there's still salt remaining. Yeah, what else?
It's chemical because you're dissolving the salt into sodium chloride ions.
Oh, so you're breaking a chemical bond because you're taking the ionic interaction between sodium chloride and you're breaking it to form water. But again, you're also not destroying it, right? So this is kind of a trick question because I would say it's sort of both. And there's a way that you can justify it in both ways. If we draw a reaction for sodium chloride dissolving in water, we would say sodium chloride solid becomes sodium chloride aqueous. That makes it look like the same as the sugar molecule, which is clearly a physical change. But what that sodium chloride aqueous really means is that it's split into two aqueous ions, sodium ions and chloride ions. Okay? So, and those ions are themselves surrounded by water molecules. So considering how, depending on how you classify an ionic interaction, if you call that a chemical bond, then you would say that a bond is being broken here. If you call that a physical interaction, because it's a physical electrostatic type interaction, then you would say, well, no, a bond really isn't being broken here, and this would be a physical change. So I think the answer is, for this one, just it's complicated. And they don't actually give this as an example in the book, I noticed, because of that reason, that some people would argue one or the other. Certainly we can see other effects, like we'll do this in lab, but certain ions, transition metals from the middle of the periodic table, when you dissolve them in water, they change color because the water molecules line up and bond with the metal and actually change its electronic properties and change its color. And a color change is usually an indication of a chemical change. So in that case, you might say, oh, that's pretty chemical. But in a case of water and salt, you clearly still have the same thing, so it's difficult to tell in that case. So these things are not always clear one or the other. But the trick is you're looking for a change in identity. Is the thing staying the same, or is it changing into some other kinds of chemicals? All right, and we'll do a chemical reaction a little bit later today. I'll get it set up when we take a break because it'll be fun. All right, so any questions about classification or changes? All right, let's get into the most boring part of the whole semester. Might as well get it out of the way today on the second day. That is units. So I apologize for the next half hour or so, which is pretty boring. But we need to know what units we're talking about and which ones are important. All right, so let's throw some out there. What kinds of things do we need to measure? Let's make ourselves a database. What kind of things are we going to need to measure this semester? What types of quantities? All right, I'll start one. Mass. What kind of a unit are we usually going to use for mass? The gram. Or the kilogram, or depending on whatever. Okay, what else? Density. What are we going to use for density? We're going to be measuring some densities tomorrow in lab. What kind of unit do we use for density? Yeah, there's lots of different units. It's mass over volume, and we'll get into density a little bit more later today. For liquids and solids, the standard density is given in grams per milliliter or grams per cubic centimeter, because 1 milliliter is 1 cubic centimeter. For less dense things like gases, we usually use grams per liter instead, because the grams per milliliter becomes so small. What else are we going to measure? Volume. What units for that? We just kind of saw them.
Milliliter, cubic centimeter.
Yeah, we'll mostly stick with milliliters and liters on the scales that we work with, but you can also use cubic length measurements. So you can have cubic centimeters, cubic meters, things like that. As long as we're talking about length, let's put that down here. Length is going to be based on the meter, centimeter, millimeter, depending on our scale. What else do we need to know about? Temperature, yep. Let's do a separate column for that. We're going to use 3 different units for temperature over the course of the semester. What are they? Yep, Kelvin, degrees Celsius, and degrees Fahrenheit. Notice there's no degree sign for kelvins. Kelvin is a unit like gram. So you can talk about kelvins, you can talk about 273 kelvins, you can talk about megakelvins or millikelvins or anything like that, just like you do with other units. The others aren't the case. The others are known as degrees, so degrees Celsius and degrees Fahrenheit. Now we aren't always careful and good about that, but you'll notice in the book, whenever kelvins are reported, there's never a degree sign. It's always just a K. So there's no degrees in Kelvin. All right, what's the difference in these 3 scales? Why use those 3? So why do we use Fahrenheit, for instance?
No reason, really.
No reason? Well, it's history, tradition is a reason, right?
Just because America is the only place that uses that word in America.
Yeah, it's been used for a long time. There are some good things about the Fahrenheit scale compared to the Celsius scale. There's one thing basically that's nice about it. Anybody know what it is? Yeah. Kind of. It's that it has the smallest units. So the difference between 1 degree Fahrenheit, the size of the degree, like between 1 and 2 or 2 and 3, is smaller than its Celsius counterpart. So I don't know if that's really helpful, but if you're like talking about the day's temperature in integral degrees, you've got a little bit more precision. With Celsius, you'd have to use decimals to get to that. I don't know if that's really a big deal or not. Let me put this figure on here so we can compare the 3. Zoom in on it a bit so we can see it better. Okay, so here's the 3 temperature scales, and it's really helpful if you have these kind of landmarks in temperature, if you know them in all 3 scales. That'll help you with solving some of the problems that we're going to do. So you should know where water freezes and where water boils on all 3 scales. Absolute zero is 0 K. You probably don't need to know that in the other scales, but certainly know where water boils and water freezes. And so there's 180 Fahrenheit degrees between water boiling and water freezing. but 100 Celsius degrees and 100 Kelvins, which means a Kelvin is the same size as a Celsius degree. Fahrenheit degree is a different size, so the conversion is a little bit more complicated. So let's take a look at how we do those conversions. First of all, what is temperature?
How much molecules are moving?
Yeah, it's how much molecules are moving. It's proportional to atomic motion. It is not a measure of energy. Energy is not a measure of energy. It's not a measure of heat. It's a measure of molecular motion, or it's proportional to molecular motion. So, so what that means is that there can be nothing below an absolute zero when molecules stop. If it were measuring energy or heat, it could always go below zero because you could have energy or heat being transferred in the other direction. And those do both have negative values. Temperature can't have a negative value because it measures the presence of motion, which once something stops, no longer exists, so it can't go negative. All right, so let's look at how to convert these. You do need to know how to do this. The easiest one is to go between Kelvin and Celsius. Anybody know that one offhand? Yeah. So the temperature in Kelvin, or I'm sorry, the temperature in Celsius, it's easier to do this way. The temperature in Celsius is the temperature in Kelvin plus 273, or 273.15 if you need more significant figures. That's the easiest because the two scales are the same, the degrees are the same size, they're just offset. One starts at 0, one starts at 273. For most of our use, we'll just use the 273. This will primarily come in when we start talking about gases, and if you go on to the second semester course when you're talking about other stuff with energy, you need that scale to not have negative numbers, so you need to use kelvins. Okay, it gets a little bit trickier when we convert between Celsius and Fahrenheit because now we've got two issues. If you look back at that scale, if we're comparing Celsius and Fahrenheit, let's just look at these two. You've got an offset, so one starts at 0, one starts at 32. And you've also got a difference in degree size. So the difference in degree size requires a multiplication or a division, just like going from a foot to a meter requires a multiplication or division. But the offset part requires an addition or subtraction. So the conversion between Fahrenheit and Celsius is going to have two parts. And probably the easiest way to remember it is that the temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. Oh, I'm getting good decimal places here. Fill that in a little bit. The minus 32 takes that offset from the Fahrenheit scale where we're at 32 instead of 0. And then the dividing by 1.8 compensates for the size of the degree. The Fahrenheit degree is larger than the Celsius degree, so we need, or I'm sorry, is smaller than the Celsius degree, so we need to divide it by 1.8 after the offset. So the opposite way, we might as well write it down. Of course, you can, we'll just manipulate that algebraically. So if we look at this one on the left, we're going to multiply both sides by 1.8 and then add 32. If we multiply both sides by 1.8, we get 1.8 times the Celsius temperature plus 32. So you need to know those equations. I think the easiest way to remember it is just remember one of those two equations, and then you can always make the other one if you need to through algebra. I usually remember the one on the left because for me, it doesn't matter, whatever's easier for you. But for me, I think about the Fahrenheit scale as being 32 off of 0. So I know I have to subtract 32 first. As long as I remember in my head, subtract 32 first, then I know to divide by 1.8 last. The order of operations here is really important. In fact, we should put some parentheses here just to be very, very clear. You need to subtract 32 before you divide by 1.8. If you don't, you'll get something wrong. Does anybody have a graphing calculator handy?
Really good.
Yeah. Thank you. Thank you. So a calculator like this understands the order of operations. So if we want to convert, let's say, well, how cold is it today? Like 60-ish? 60 degrees Fahrenheit to Celsius, and we type in 60 minus 32 divided by 1.8, we get 42. So 42 Celsius, is that reasonable?
Yeah.
Think about that. It's pretty high. What's body temperature in Celsius?
37.
37. So is 60 degrees like it is outside way higher than body temperature? It's not. So that means we did something wrong. And what we did wrong was by typing it in without parentheses, the calculator automatically does the division first, followed by the subtraction. So what we should have done was 60 minus 32 in parentheses, and then divided by 1.8. Now we have 15.5, which is a more reasonable number.
You sure it's not supposed to be minus 273? This doesn't make sense. Because like what 0 degrees Celsius is 273?
Oh, yeah, should we-
Oh, yeah, yes, you're right. I'm sorry. You're right. Thank you. Yes.
Oh.
Thank you. Yeah, because 0 degrees Celsius should be, or 0 kelvins should be minus 273 Celsius. Yes, thank you. I'm sorry. So you would add 273 to the Celsius for that one. All right. So you can do some kind of temperature conversions. What other kind of units are we going to run into this semester? Ideas? Yeah. Energy. We are going to get into some energy. Now, actually, the way we do this class, most of our energy calculation stuff comes in the second semester. So we're not going to get to much of that. But what are some of the energy units that we may see? Joules, calories, those kinds of things. We won't see much of that this semester. That's more in the second semester course. All right. Let's talk about our metric prefixes. You should know these. Rather than write them all down, again, I'm going to copy them from the book so that we all have them there. Oops. Okay, here they are. I'm going to skip the real big ones. We're not going to use those so much, but well, I guess we got to put them all together here anyway. I'll tell you which ones you need to know. All right, so you should know these. If you want to know those other extreme ones, that's fine. The reason for those, those prefixes are what we consider important. The picometer is just smaller, or is right on the scale of an atom. So atoms are in the hundreds of picometers usually. So below that, you're talking about subatomic sizes, and that's not going to concern us too much in this class. And then up into the giga and tera Again, those are prefixes you probably already know from computers and stuff like that. So keeping the order in mind is going to be somewhat important here.
What do we need terras for?
What do we need terras for?
Yeah.
Like computer memory is where they come up a lot.
I mean, like in this class.
In this class, I mean, it just depends on the quantities of things. So if we're talking about teragrams, for instance, well, I'll give you an example. We do calculations about climate change and greenhouse gases. That is often expressed in either gigatons or teragrams in the atmosphere, because you're talking about pretty large quantities. So that's one situation where that comes up, where we're looking at carbon. Okay, the way I remember these is just in order, and then knowing that each one is a difference of 10 to the third. So if you know the order, tera, giga, mega, kilo, and then the kind of exception ones here, I don't know why they threw these in the same chart, because it kind of throws off the pattern. But if you exclude those two, then everything is just 10 to the third difference. So each time, if you want to do these conversions, you can just go by 10 to the whatever. So let me give you an example of how I would use that. I can't remember nano. I can't remember what the factor is for a nano conversion. I know it's small, but I don't know. But I know it goes from just regular nothing, it goes milli, micro, nano. So that tells me I've got 3 10 to the third steps to go. So that means nano is 10 to the 9th or 10 to the minus 9. There's 10 to the 9th nanometers in a meter. So if you remember the order, you don't necessarily have to memorize every single number. You just know that you jump by 3s, excepting those couple weird ones. We're doing okay on time here. Okay. We'll do some practice with these. We'll do plenty of practice with this stuff. Let's first talk about density, because that's our last piece of this idea, and then we can take a break and come back and do some practice. Density is going to be really important for our lab tomorrow. We'll define density as the amount of matter in a given amount of space. So how much space does a certain amount of matter take up? In order to figure that out, we use a density measurement. So how do you measure density? If that's the definition, how are you going to measure what something's density is? So you need some way of measuring the volume, and displacement might be a good way to do that. That means that you'd say take a graduated cylinder with a certain amount of water, you submerge whatever you're measuring in the water, and you measure how much the water level has gone up. And that's a good way of, displacement is one way of measuring volume. Another way would be a direct measurement of volume. If you had something like a cube, you could measure the sides or a side and then multiply to get the volume. But somehow you need to know the volume. And then you measure the mass of that known volume. Okay. So the equation for density, as we already talked about, is mass divided by volume. The mass and the volume can be any units you want, but that's the density that you're going to get. So like we said in standard and lab, what we're going to use on Thursday is going to be grams per cubic centimeter or grams per milliliter. But depending on how you measure the density, you could have something different. You could have pounds per cubic inch, something like that. Pounds per cubic foot. You could have pounds per gallon. That's an important measure of density when we talk about fuels, because we usually measure our fuels in gallons. And so the pounds per gallon is going to be how we measure that. Okay, so is density fixed, or can density change for a given substance? Like, let's say water. Is the density of water always the same, or does the density of water change? Stays the same? What about ice? Do ice and water have the same density?
No.
No. Which one's more dense?
Water.
Water, which is weird, as we said before, because usually the thing with the less density, or the lower density, is the liquid. So it goes like gas, liquid, solid. Water is a little weird like that. But actually, water can change its density too. Density changes with temperature. Density can also change with pressure, not so much with liquids and solids, but certainly with gases. So density is not fixed. Density does change. What do we generally take as the density of water? Do we know what the density of water is, the value? What we usually say? Not quite. And just in grams, maybe in a different unit, it is. In grams per centimeter, density of water is about 1 gram per cubic centimeter or milliliter. But that's with one significant figure. Let's see if there's well, it's on Blackboard. So one of the things that we'll need for tomorrow, as long as we're talking about density, we have a chart here of the density of water versus temperature. So when we say that the density of water is 1, we're really saying the density of water rounds to 1 depending on, at room temperature, depending on the number of significant figures. It's actually at lower than room temperature that it's 1. So if you have 1 significant figure, 2 significant figures, even 3, so 1.00, in most cases, water is going to be 1. But if you go beyond that, as you can see here, it changes. So this table, the way we would read this is like, let's say it's 20.5 degrees in here. So we go 20.5. The density of water is 0.998099. And we're going to be precise enough with our measurements tomorrow using volumetric pipettes that we can actually use not quite 6 significant figures, but we should be able to get 4 or 5. So we'll need those temperature corrections. If you're only dealing with 2 or 3 significant figures, then you can just say the density of water is 1, and that's good enough. But that's why, like we talked about yesterday, your measurement precision is really important there. All right, so that's the various quantities that we've discussed. So next we're going to look at how we use these in calculations to convert from one quantity to another, and including using density in that. So this seems like a good stopping point. Let's see. It's a little early, but that's all right. We'll take a break. We'll come back at, let's say, 12:25, so a little more than 15 minutes. And we'll have some practice problems and work through some of that, and then talk a little bit about atomic structure. And we'll be done.
So are we like halfway through the day so far?
I mean,
Like,
we're a little before halfway, I guess, because we're done at 2:05.
Yeah.
Yeah. Cool. All right, so let's say we have a problem like this, which is the first one on that sheet that I handed out. You've seen these sorts of things before? You like these sorts of problems? Not so much? No? Some people are like, yeah, no. Yeah, these can be tricky. They can be, if you pick your parts wrong, they can have some trouble, but we're gonna work on this a bit today, and we're gonna keep working on it throughout the semester because most of the math type problems that we need to do this semester are kind of like this. And so if we get good at these types of problems, then you're set for pretty much all the chemistry math type problems you need. So let's start that. So I'm gonna show you how I would do a problem like this. And if you've learned another way, there's all kinds of different tricks people have for doing these things. If you have one that works great for you, just stick with that. You don't have to do it my way. But here's a way that I like to look at it. So the way I like to think of these problems is like a map. Like you're starting at one place and you're trying to end up somewhere else. And so you have to take a particular path to get from where you started to where you've ended up. And the path is going to be defined by the units that we use. So in this case, a Tour de France, one stage is 129 kilometers. How many miles did the bikers ride that day? So our path is going to say, well, okay, we're starting with what we're given, which is kilometers. So we're starting with the unit of kilometers. And we're going to go through some number of conversion steps to ultimately end up at miles. Now, in this particular problem, we have a conversion listed right there from kilometers to miles. So that's it. It's a one-step map, kilometers to miles. We're given the number of kilometers. We want the number in miles at the end. So it's one step. As we go through some of these, you'll see not always one step. But thinking about it this way and thinking about it units first and then numbers is going to help you keep it straight and help you make sure that everything lines up properly. All right. So how do we do that? Once we've set up our map, then we write identities, which means multiplying by 1, in such a way that the units can convert from one to another. So I start with whatever number I'm given first, in this case 129 kilometers. And I want a fraction here, so I'm just going to make it over 1. And then I want to multiply it by some factor that can convert between kilometers and miles, which means I put the unit that I don't want anymore on the bottom and the unit that I now want instead on the top. So kilometers on the bottom, miles on the top. That means that I can cancel the kilometers. And then I actually wait until the end to fill in the numbers. The reason I do that is because if you've got all the units set up, then all you need to do is match up the number to the unit. A common mistake that I see on these is just kind of dividing instead of multiplying, or couldn't remember which number goes on top, which number goes on the bottom. If you try to always remember that, like, oh, I always remember that in density we put the volume on the top or whatever, that's going to get turned around in your head, or you're going to make a mistake on an exam or something. If you just follow the units, so kilometers cancels to the bottom, miles on top, you can't ever go wrong. As long as you follow the units, they'll always be in the right place. So our last step is just to pair those units up with the numbers. 1 kilometer per 0.621 miles. And then we evaluate by multiplying through whatever's on the top, dividing whatever's on the bottom. And then evaluating our significant figures. In this case, there would be 3 from both of those numbers. So 80.1 miles. All right, so you've done stuff like this before? All right, we'll keep working on it. So let's look at what happens when this gets a little bit more let's say complicated. So go ahead and pull up this sheet, and we're going to look at the front of it, which is the one that starts with this problem. And take a look with your whoever you're sitting with, or if you don't want to work with that particular person, jump around to somebody else. If you want to stick with lab partners, or if you want to work as an entire table of 4, that's fine too. And try just the next 2 problems, then we're going to talk about it together. So number 2 and number 3. And just so we remember, what is the SI unit for mass? Kilograms. So when it says convert 10 grams into the SI unit for mass, it's asking for kilograms. See if we can do those next 2.
Both these This stuff is all part of it.
Well, you know if you're stuck.
Yeah, I mean. That's going to be 63. That's like that. This one.
That's it. Yeah. But
That's
okay.
what I
I
learned
think I
in high
get an idea of
school.
what it is. Yeah.
I just wanted to know that they won't play the point there. I was originally.
Yeah, that's what I would do too. Dividing by 1,000.
Yeah,
But it's this dividing by 1,000 is the same as multiplying by 1,000. What is this?
It's like this is like this is your base. This is like different. I don't know. I like this. Like this is centimeters, kilos.
I get balance at the end.
Yeah.
It's the 800. They're at. Okay. Yeah. Yeah. That works. There's easier ways to do it here.
This class is very good. Like, based on this.
Right. Yeah, the way you do it also works. You save your couple
Okay.
button pushes. It's good that way. Oh, actually, that is a problem.
Some policies are changing.
And then the second half.
Oh, it's meters, yeah, okay, you're right. I thought it was centimeters. Well, I mean, that's, you can do it that way. So, it's 5 years of dimensions.
Right.
You're gonna do some stuff like this. Yeah.
Right.
So,
Do what she asked me
you
to
got
do.
it correctly, but there's 10 or it's
Like she starts off. Yeah.
just think about what's bigger than the other one, and then more of the smaller ones. Really? All right, let's take a look at these two, and then we'll move on. So this one we're going grams to kilograms, which means we're going to set up the equation like this: 10 grams, and then grams go on the bottom, kilograms go on top. And then we need to ask how many grams are in a kilogram or how many kilograms are in a gram. Now, this is the main source of error that I saw walking around, is just flipping, not on this problem so much, more on the next one, but flipping the numbers, getting the wrong one on the top or the bottom. So the first question to always ask yourself is, which unit is bigger? So which unit is bigger, a gram or a kilogram? A kilogram, yeah. Kilogram is bigger than a gram. So if a kilogram is bigger than a gram, that means you need more grams and fewer kilograms to have an equivalence. So whichever number is bigger is always going to go on the bottom. It's always going to go next to the one that's smaller. Does that make sense? I said that backwards a couple times.
Bigger number with smaller.
Bigger number with smaller unit, yeah, because you need more of something. So, because there's two ways to do this. You can either say that there are 1,000 grams in a kilogram, or you can say that there are 0.001 kilograms in a gram. Those mean the same thing.
Just nicer to do that.
I agree, but however you like to do it is fine. So if I know the numbers are 1,001, and I'm trying to remember which one goes where, just say the sentence to yourself in your head and see if it makes sense or not. Are there 1,000 grams in a kilogram, or are there 1,000 kilograms in a gram? Well, if the kilogram is bigger, there must be 1,000 grams in the kilogram. And sometimes just kind of talking that out will help you keep that straight. So once that's all straight, then we can evaluate this and see that it is 0.01 kilograms. Good. All right. So next one, it's really the same kind of problem, but because nano is a bigger, smaller number and we have to use powers of 10, it seems trickier. But we're going to go about it the same way. Nanometers to meters, which means we start with 5.6 nanometers. And we find a factor that puts nanometers on the bottom and meters on top so that we can cancel those nanometers. Yeah?
For number 2, don't you want to convert it to the right suffix?
Yeah, these problems don't have a great... So like technically that is right because there's one significant figure because we don't know if the 0 is significant or not. But you're right, it should be more precise. Sometimes when we're given problems, we're not given precision, so we have to kind of guess. But yeah, a better way to report that would be 1 times 10 to the minus 2, or if we thought that 0 was significant, we might call that 1.0 times 10 to the minus 2. Yeah. This one we can be a little bit more sure of because we know 5.6, we know we're going to have 2 significant figures. All right, so now we have to ask how many nanometers are in a meter. So if you come across this on a quiz next week or something, and you got to remember, oh, what's the number for nanometers? You're not going to have the table to look it up. So how do you figure it out? What I would do, and you can even just write this somewhere if you don't, you start wherever you're going to start, and then you just count down the prefixes in order. So you go milli, micro, nano. However you want to remember them is fine. This is how I do it. And then it's 10 to the 3 each time. So 10 to the 3, 10 to the 6, 10 to the 9. Now, whether that sign is negative or positive just depends on which unit is bigger. So if we think of that as 10 to the 9th, we would say there are 10 to the 9th nanometers in a meter. Does that make sense? Because we know the nanometer is smaller than the meter. So there must be a whole bunch of them, 10 to the 9th in a meter. If you think of that as 10 to the minus 9, which is how it's listed on that table from the book, then you're saying 1 nanometer is 10 to the minus 9 meters. So 2 different ways of writing that equivalence, and we can write it right here. So we can write that that 1 nanometer equals 10 to the minus 9 10 to the minus 9 meters, or we can write that there are 10 to the 9th, positive 9 nanometers in 1 meter. Again, I always stick with the positives. It's just easier for me to keep it straight in my head, but however you like it is fine. Yeah. I mean, like the positive exponent, yeah. But however you like to do it is fine. So if we stick with that, we'd say 10 to the 9th nanometers in 1 meter, which means that our answer is going to be 5.6 times 10 to the minus 9 meters. And with these types of problems, there's usually a pretty good way of checking yourself if you just look at the reasonability of that answer. Like, is it reasonable? 5.6 nanometers is a tiny, tiny amount. So in meters, that should be really small, 5.6 times 10 to the minus 9. So if we had flipped that, or if we had messed up, if we had used minus 9 instead of 9 or something, we would have gotten a really big number, 5 times 10 to the 9. That can't be right. 5 times 10 to the 9 meters is like, I don't know how far it is to somewhere in space or a planet or something. I don't actually know. But that's a lot of meters. So that's definitely not 5.6 nanometers. Save file. Oh, yeah, that's right. That's fine. Okay. Questions about those two? Okay, these next couple, especially the 5 one, are a little more complicated in that they were going to require multiple steps. So multiple ways of getting from one thing to another. So let's look at number 4 together, just to get it kind of set up, and then you can work with your partner on the next two. So how long would it take to fly from Denver to New York, a distance of 1,631 miles, at a speed of 810 kilometers per hour? And we may need to look up some information here also. So first we want to know, what question are we being asked here? The question is how long. So that means that our answer is going to be in what type of units? Hours, or some sort of time at least. Based on what we see in the problem, probably makes sense, hours. So that means that when we set up our unit plan here, our very last step is going to be hours. We're going to get to hours. All right. We're starting with miles. Miles. We're starting with miles. We're given the distance. You could also start with the speed, but it's going to be a little easier if we start with the miles. So we start with miles. So now we have a situation where there are two different types of units here. We're starting with a distance measurement, and we want to end with a time measurement. So that means we need some sort of a factor that tells us how much distance in a certain amount of time. Do we have that? We do. What is it?
810 kilometers per hour.
Yeah, so we can go from kilometers to hours. And we can plug that in now to our unit plan because we know we have a factor here that tells us how many kilometers are in an hour in this case. Now that's not like an identity. That's not saying there's always that many kilometers in an hour, but for the purposes of this problem, that's how many you can go in an hour. So we can consider that as a conversion type problem. So see how I can plug that in? So that allows us to switch between time and distance. All right, so now can we convert between miles and kilometers?
We have it there at number 1 at least.
What?
Yeah, we have it at number 1.
We've got a number. Oh yeah, that's right. We've got the conversion up there. So yeah, we may have to look that one up if we didn't know that, but at least we've got it in there. So we're set. So we can set up a conversion to go from miles using this to go from miles to kilometers and then kilometers to hours. All right. So see if you can set that up with your partner, plug that in and get those numbers. By the way, for the purposes of this class, in terms of what you need to memorize, you need to know all those metric prefixes that we talked about before. You don't need to know any of these conversions to go between systems. So you'll always be given like how many miles are in a kilometer or how many gallons are in a liter, those sorts of things. We'll always give you those. So let me know if you're stuck.
I would actually do all those together, so don't even evaluate that first. Just keep going on miles. Do it all together as a quick thing. So, yeah.
So try setting up the units first and then putting in the numbers rather than thinking about them as discrete blocks.
Yeah.
For next week. And then like. But in terms of just like access to rights.
Oh, you read it. You read it or have it?
So if you get that one, move on to number 5. Number 5 has even more steps. See how you can do it that one.
Oh, no, I just skipped right that. No, it's easy. Yeah, I don't know what the answer is.
I would say this, I need some sort of conversion.
Right, right.
There's no little bit of something, it's how you over that. You know the definition for miles to meter?
Use this.
Ooh, you're right. Yeah.
So then next one. So I did like this swap because it's mine one meter equals 0.062.
Yeah.
Our swaps, our so it's one
And
meter,
numbers.
yeah.
Okay.
Yeah, I mean, if you're bored, you can.
You multiply divide, I just forget to say, I think like the lowest number of savings that we use for. Right. These six fixes, this can just be one business. Okay, you guys still need a 6.3 for like, for number 5.
It actually you did it for
I read it in 3 times there. There's just 4 hours.
You know what, I was debating whether or not actually
Three.
3.00, yeah.
Oh, 3, okay, there we go.
That's, yes, it's. Well, sure. Yeah. I don't see
You should record it as well. All right, looks like some good work on these problems. If you're still working on it, go ahead. I'm just going to take a look at this first one. And actually, I'm gonna do it down here because there's a little more room here. So we already set up the map of how our units are going to work out. So then you can set up the equation without even looking at any numbers yet. You can just go miles, and then miles to kilometers, and then kilometers to hours. Let's do H, I guess. Kilometers to hours. Then we just fill in the numbers. So if you do the units first, there's a better chance that you don't get something flipped backwards when you put in the numbers. 1631. Then we've got miles and kilometers was up here on the top here, 6.621 miles and kilometer. And then this is given in the problem, 8, 10, and 1 hour. So 1631 divided by 0.621 divided by 810 is 3.2. What you got? Okay. We would report that with 2 significant figures because of the 810, because we don't know if that 0 is significant or not. If you reported it as 3.24, that would probably be okay, again, because of the ambiguity in that number. All right, should we do this one? Or you need a little more time to work on it? You're good? Okay. So this one, there's a lot of stuff going on in this problem, and part of the challenge of these is just figuring out what you need. So one thing to do is just jump to the question first. How many hours? So we know our final unit is again going to be hours. So where are we starting here? Then we can read the rest of it. Radio waves travel at a certain speed. If Neptune was 2.75 billion miles from Earth during these transmissions, how many hours were required? So we've got 2.75 billion miles away, and then how many hours are required to get that distance? So we're going from a distance to a time. Miles to hours, but our conversion here has got to be meters per second. So that the thing that we're given that gets us between the distance and the time is meters and seconds. So that means we need to get our distance into meters, and then our time is going to get us from seconds to hours. So we can go seconds to hours, and hopefully we can go miles to meters, and then meters to seconds. But maybe we don't know the conversion from miles to meters. What we have is kilometers to miles. So we can take a little detour here and go miles to kilometers to meters. So this is what I mean about building a map. You can always kind of revise it, figure out how to get from unit to unit based on the numbers that you have or that you know. And if you know these conversions in your head, you can always use those too. But this is what we have right now. So then we can set it up. And as you get better at this, again, with more practice, you'll be able to take some shortcuts and figure out some other ways to do it, and that's great. For now, we're doing it all out the full way here. So we're going to go miles, kilometers, meters, seconds, and hours. And if you didn't know how many seconds in an hour, you could go seconds to minutes to hours. So then filling in the numbers from the problem, 2.75 billion miles. To me, the easiest way to do that is just keep it in scientific notation since it's billion miles. And we know we have some other stuff like that around here too. So that's going to be 2.75 times, so million is, or 1,000 is 10 to the third, million is 10 to the sixth, so billion is 10 to the ninth. Again, if you remember the order is just like with the prefixes, and you know it jumps by 3 each time. Then we've got 1,000 meters in 1 kilometer. 3.00 times 10 to the 8th meters per second. And there are 3,600 seconds in an hour. 60 times 60. Okay. So then we evaluate that. Now, evaluating scientific notation. If you have, a couple people have asked me, so I guess it's worth talking about. Can I borrow a graphing calculator? If you have one of these graphing calculators, it's a really nice, easy way to do scientific notation. You don't have to put the number in and then times and then 10 to the whatever. There's this little EE. It's like 2 capital E's. So you can go 2.75 E, and that E means times 10 to the, and then you just put 9. That saves you a little work, and it keeps it all together, so you don't have to worry about the parentheses and order of operations and all of that. So if you have that, you can do that. What if you don't have that? You can do it based on what you remember from math class, that if you divide exponents with the same base, you can subtract the exponents. So I see I've got a 10 to the 9th on the top and a 10 to the 8th on the bottom. So 9 minus 8 is 1. So I can just put that in as 27.5 and skip that 10 to the 8th on the bottom because my calculator doesn't have scientific notation. So I'm going to do that as 2.75 times 10 to the 1, times 1,000, divided by 3, divided by 3,600. And I get 2.54. Is that right? Is that what you got? Or did I do something wrong? Oh, I did do something wrong. I forgot something. Everybody see what I forgot?
Is it like the miles to kilometers?
Yeah, I totally forgot to put something in here. So you see how I went miles to kilometers? But there's no term here that goes from miles to kilometers. If I was following my units closely, miles don't cancel with kilometers. So that's wrong. Let's fix that. Can I move this over a little bit, maybe? I need a term that goes from miles to kilometers. So that's going to be 0.621. Now my units should work, right? $4.1, they look better? All right, how many significant figures do I report here? 3. So that's going to be 4.10 hours.
But what about the 3,600? Aren't there only 2 significant figures?
Oh, good question. What do you think?
4.1.
Notice my last term, 3,600. So aren't there just 2 significant figures there? There's not. There's something else going on here. Let's talk about this. Let's jump back to the notes so that they're all together. We didn't talk about this yesterday in our significant figure review. There are two types of quantities that we're going to deal with that have different consequences for significant figures. And they are measured numbers and exact quantities. So a measured number is like a measurement that you would make. And these have the kind of typical significant figure rules. So let's say you make a measurement, that's where that word comes from. But it could also mean some of these conversions, like 1 kilometer equals 0.621 miles. If we look up the actual conversion here, we can get a whole lot more numbers there. So when we say 1 kilometer is 0.621 miles, we're kind of truncating that number or rounding, and we're saying we are reporting this conversion to 3 significant figures. But there are other types of conversions that doesn't apply to. So this one has 3 significant figures. Other types of conversions are known as exact quantities. So for instance, 1,000 millimeters is 1 meter. So how many significant figures does that have, 1,000 millimeters in a meter? It's kind of a trick question. It has infinite significant figures because it is an exact quantity. There are exactly 1,000 millimeters in a meter. So you can make that number 1,000.000000, as many numbers as you want. And exact numbers like that, so when you're counting something, an exact number that you count has as many significant figures as you want it to have, which means we don't consider them in these types of calculations. Some other examples of those are like the time ones. 60 seconds in 1 minute. There are exactly 60 seconds in 1 minute. Not 60.0, not 60.00, not 60.000, exactly 60. Which means we can assume there are as many significant figures as we want. And that's why that number doesn't, yeah. Other things, you know, like anything that you count is considered an exact quantity. And anything that you measure is, you have to deal with the significant figure. So in general, and there are some exceptions here, but in general, when you go between measurement systems, like between metric and English units, those significant figures are important because they're all kind of big numbers, you know, weird numbers with decimal places. When you're within the same system, generally they are exact quantities. So if you say there's 12 inches in a foot, there's not 12.0 inches in a foot, there's exactly 12. So you can assume that's as many significant figures as you want. So these exact quantities that we have in our question here the 1,000 meters in a kilometer and 3,600 seconds in an hour don't count for our evaluation of significant figures because they are exact quantities. Only these numbers, the speed of light, 3.00 times 10 to the 8th, and the initial number, excuse me, 2.75 billion miles are going to count toward our significant figures. But thanks for asking that, because it's good that we talked about that. All right. Let's go on to the next two. And then if you get those two, go ahead and flip it to the back. The questions on the back are a little bit more review from last, well, the very first question isn't, but questions 9, 12, and 13 are some significant figure and measurement review stuff from yesterday. And then there's some stuff about density and temperature. So go ahead and keep working on this. Let's work through the whole thing, and then we'll come back and put it all together in about, I don't know, 20 or 30 minutes, however long it takes.
So, you want to do this?
kind of. So it's, yeah, it's the other way around. So this one isn't a straight ahead thing. This is one per side. So you have to calculate the columns based on
I didn't do that. So just inches.
So inches will have to go to the centimeters first and then centimeters.
Yeah, one more thing, sorry. The number 7 is a little bit different. It's not a straight ahead conversion question. You have to think about how to calculate volume. So for those of us who don't remember geometry very well, how do you calculate the volume of a cube? Yeah, you multiply side by side by side, or side cubed. So like whatever the length of the side is, times itself, times itself. And then there's one more thing you need to know for that question. How many cubic centimeters are in a milliliter? 1. They're the same type of unit. 1 cubic centimeter is 1 milliliter.
You have to convert inches into centimeters.
Well, to milliliters. So to do that, you have to recognize that 1 milliliter is the same as a cubic centimeter. And convert inches to centimeters. So you have to look up conversion between. Okay. Yeah, this one, the conversion isn't given. You have to look up a conversion between.
And that is 2 point, you want to go from.
It's 2.52. 2.5 parties.
I don't know, I don't know this.
Yeah, this one was the third. Or take out the oh, cancel that. No, these are the original. Right. Oh, right, yeah. Oh, yeah.
Well, in this case, this thing is, this, that's a really cool thing. So in my, so the unsacred, I got 302.63, we did 302.6.
So you just want to
All right, well, it's like one decimal place, one number after the decimal place is what I want. Okay, there's in these cases, in this case.
I got 16.
I'm gonna check this out. Oh. Well, I just wondered if I did the calculation for
I don't know.
okay, so first off,
Wait, do you think we have to
just look at these things, 2 liters, 6,
Oh,
just
yeah.
6, so it's like this thing, and it's one of those, something like that.
So you finished.
And this thing I'm pretty sure.
No, that's.
Yeah.
So you're going like this.
Oh, my goodness.
You're not.
No, but the especially first, the year's canceled.
Well, one,
So you're gonna,
B, I'm ready to move the one.
and then you're already got it.
So you guys will.
Or keep centimeters, sorry, and then all of it.
Oh, yeah, yeah. I'm sorry, I didn't, I thought I heard that was the best.
That's the volume.
This is yours. Oh, yes, I thought this was, I didn't know. Okay, so yeah, so you just gotta take that.
No, let's do this.
Okay, yeah. So we want to measure.
Yeah, there's one thing I just kind of bad at, it's just significant.
Yeah, it's all blue. Patients are right.
Well, I think that's already the crush. The problem was when I advertised that it was already there. Because I know the main aspect is just like the number themselves. Okay, like this specific number, and different rules for specific numbers.
You mean like what are the zeros and one?
Yeah, simply that.
Yeah, it's just zeros at the end of the number after the decimal system. Zeros before the number, even after the decimal system.
So 0.0036 is 2, so 36.00 is 4. Is it?
Right, but then you have to go on.
It's 3600, you do that.
That's the figure. Technically it's 2. Because the 0, 0. Plus the decimal place. But, so a number like that, you really want to be precise. 3.6 times 0, 0.
Yeah, I'm more concerned about 3600, that's, it's so ambiguous.
So you have to go the way they do it in the book or like on the online report is they'll use, you can assume those zeros are not significant unless you actually. Then all of these.
Then it was 6.
But the tricky thing is like, okay, so let's say you have 3600, but because of your measurement, you want 3 significant figures. So you have to write that in scientific notation, because otherwise there's no way of showing that this is 0 are significant but not the last.
It's like 1.36 thing. And since you have the 7 meters cubed, it's not, just put that.
Well, first of all, you can't convert milliliters. This is the Q one? Yeah. Yeah, so you need to say, okay. Q is which means the volume of that is it's 1 cubic inch. So then you need to convert those inches to centimeters. And then you get a given centimeter. But you have to use that 2.5 meters per inch. Okay. So once you get sent, so you make the inches like this.
What did you do to figure out that it's not for Yeah, I have a question.
Yeah.
I'm confused how to like, this is just for yeah.
It was 16.
But the two units don't hit them. Because then you want to have this is for.
Right, so this one, you have to, they only cancel with one at a time.
Let me show you what that looks like. There's been a few questions on number 7 about the cube thing, so I want to take a look at that one. So there was a question about how to do this as a regular, like straight up conversion question, which you can actually do once you find the volume. Whoops, no, not this one, sorry. The one before. All right, so anyway, it's 1 inch on a side. We want to go, so you take your cube. That's 1 inch by 1 inch by 1 inch. So that means that the volume of this cube is was it 1.00? Yeah. Is 1.00 cubic inches. So an inch times an inch times an inch is a cubic inch. Okay, so how do you convert a cubic inch to a cubic centimeter? You can go, so let's say you want to go, let's make our map again. So we want to go cubic inch to cubic centimeter. Now we don't know the factor that goes between those two, but we do know what goes between an inch and a centimeter. So we kind of have to do this 3 times to get to the right conversion. Because if you look at, follow how the units work out, if we put inches on the bottom and centimeters on top, we cancel one of the 3 inches, but not all 3 of them. So we have to do this 3 times. You can either write it out like 3 times separately, or you can just say, well, if we cube this, then we'll have taken care of all 3 of those inches, and we'll end up with cubic centimeters. So the answer here, all of those would have canceled, and we'd end up with an answer whose units are in cubic centimeters. You see how that works? So when a unit is squared or cubed, you have to divide it multiple times to get rid of all of them. In this case, it comes out to 2.54 times 2.54 times 2.54 is 16.4. And since a cubic centimeter is a milliliter, that's also 16.4 milliliters. So for number 7 then, this is one of the metric prefix things. How many centigrams are in a gram? A 100, just like centimeters. There's 100 centimeters in a meter. So there's 100 centigrams in a gram. So a centigram is smaller than a gram. So you can convert that to grams and then put it over 16.4 to get the density. Does that make sense?
Yeah, that's fine, because it's 0.01 grams per centigram. Okay. Yes. So you know, well, what is the volume of less focus, whether it's empty or not? Subtract and then, yeah, convert to milliliters, but it's one. So that's,
So yes. So it gives you the density of. Oh,
That's just. That's just.
you're looking.
centigrams.
Well, you said that like, when you put anything, everything should be that.
It doesn't quite work out. Well, so look at how you want your units. So you convert centigrams to grams. Then you want to end up with milliliters, right? Or grams per milliliter. So that means, yeah, so that means you want to just put that on the bottom so it just stays. So this, yeah, that's because that's going to be milliliters. And you don't want to end up with that. I just want it to stay on the bottom. So you just put it at the bottom like the plus. Yep. You would go 1 past 2 because it's estimated. Yeah.
Just convert it. The, All right. Looks like keep working. But I want to start going through some of these other ones.
So this number 7, if you want to go through this one, you can also do this like a conversion question, although looking around it seemed like a lot of people didn't, which is also fine. The density is grams per milliliter, so you want your end result in grams divided by milliliters. But you're starting with grams, 504, or centigrams, 540 centigrams. So the way the conversion is going to look here is you're going to convert centigrams to grams, and that leaves you with grams. So if you want grams per milliliter, there's no unit to cancel. It's just, you're just going to add the milliliters in the bottom. So you're not, in this case, you're not going to multiply by a conversion factor. You're just multiplying by a factor that puts the milliliters in the bottom. So however many milliliters we have, which is the cube, the volume of the cube. In this case, that's because we already calculated that, so that's 16.4 milliliters. And then there's 100 centigrams in 1 gram. So that makes the density 0.329. Is that what you got? Okay. All right, let's take a look at this density problem. So you got a flask, you weigh it, then you fill it up with water, you weigh it again, you get these two numbers, and we want to know what the volume of that flask is. So what'd you do for this one? So we know how much water is in the flask, yeah?
So we subtracted the grams from the total water by grams.
Yep. So you're going to go 283.2 minus 121.3. 161.9. And that's grams. So that's the mass of water that was in the flask. But since the density of water is 1 gram per milliliter, we're converting this by multiplying it by 1 gram per 1 milliliter, so it's just 1. So that means the volume is 161.9 milliliters because the density is 1. So all that water that was used to fill up the flask had a volume of 161.9 milliliters. All right, what would be the mass of the flask when filled with carbon tetrachloride? So we still have a 161.9 milliliter flask, but now our density has changed because we've got carbon tetrachloride, which is heavier. So 1.59 grams per milliliter, milliliters cancel. And we've got 257 grams of carbon tetrachloride. Questions about that one? So this is kind of an unusual one. This mercury thermometer has gradations that are, the big numbers are in 1, so 21, 22, 23. What are the smaller lines? 0.2, yeah. So does that mean that we estimate a digit past the tenths or not? Yeah, we still do. We still go 1 digit past wherever the tick marks are. The fact that they're in 2s instead of 1s changes our precision level. Yeah.
For 8,
Yeah.
would you add the weight of the flask?
Oh, that's a good question. Yes, I guess you would, because it's asking for the mass of the flask when filled. So yeah, so that's how much carbon tetrachloride we would have, and then we'd add it to the 121.3 gram flask. You get 378 total for the filled flask. Thanks. All right, back to the thermometer. So if it's graded in 0.2 instead of 0.1, that means that instead of being plus or minus 1 on that final digit, it's maybe plus or minus 2 or plus or minus 3, depending on the instrument. But we still do estimate that final one. The other weird thing about this one is the upward meniscus instead of the downward meniscus. But again, you go from the tip of the curve, whether it's the top or the bottom, you're still going to the tip of that curve. So in this case, what do you estimate that one as? 22.25? Does that sound about right? Yeah. So there's a little bit larger range of possible correctness here. If we're really looking at that tip there, you could probably see that all the way up to 22.3 even. So that means that our precision here is more like plus or minus 2 or plus or minus 3 on that final digit instead of plus or minus 1. But this number should still be reported to 4 significant figures. All right, and let's do some conversion. So C to F, we're going to go 1.8 times 22.25. And that 1.8 is an exact number. It's 9/5. So we don't have to use that for 2 significant figures. We use our measurement for significant figures. And then plus 23.15. Wait a second. I'm mixed up. It's supposed to be Fahrenheit, right? So that's 32. Again, an exact number. So 72.05 degrees F. And then in Kelvin, we would add 273.15. Get 295. And even though the calculator reports that as 0.4, we should report it as 0.40 kelvins. Temperature unit conversions should not change your precision. So they shouldn't change your significant figures nor your decimal accuracy there, your number of decimals. Yeah. When you're going the other direction. So when you go from Fahrenheit to Celsius, you subtract 32 first and then divide by 1.8.
Is there like a reason why it's not the same rule for both?
Yeah. Where's our notes here? Oh, over here. Yeah, it's the algebra here. So if you think about these two numbers have to be, or these two equations have to be equivalent. So when you multiply each side by 1.8, you're not also multiplying the 32 by 1.8 because that's happening first. You're adding then the 32. So it has to do with how one is turned into the other one via algebra. All right. Another temperature conversion, I'll assume you're okay with that one. Let's look at significant figure review for those of you who didn't stick around last time. When you're adding, you use however many decimal places, the lowest number of decimal places. So this is going to be 100.53 plus 98.7 plus 103.4. And we would round that to the tenths because this number, the last decimal place is the tenths, or the lowest. I guess these both do, but the fewest number of decimal places is the tenths, and so that's where you would round it. Same thing with the next one, 0.253 plus 0.0361 plus or 0.17. And we round to the hundredths because of the 0.17. So 0.46. The difference between the two numbers, 302.6 minus 0.46, it's going to be 302.1. Yeah. Again, we round when we subtract to the correct decimal place. And then when we multiply, we use the fewest significant figure. So 302.6 times 0.46. We're going to round that down to 2 significant figures because the 0.46 only has 2 significant figures. So that's going to round to 140, or more clearly, 1.4 times 10 to the 2. Since 140, that 0 can be ambiguous whether or not it's significant. Is that what you got also for those of you who made it that far? All right, so we got about 20 minutes, a little under 20 minutes to go. We're not going to go into the new material, but I do want to look quickly at the lab for tomorrow, just so you're prepared. So as we talked about yesterday, each week you want to be prepared for lab. To be prepared for lab, you're going to be checking out the lab schedule, figuring out what lab we're doing, and then printing out the necessary material and completing any pre-lab activities that are specified. So in this particular lab, it's the R volumes of pure substances additive. So we go over to Blackboard, you go to labs, find that particular lab, it's right here. And then we've got our procedures, density of water, and data tables. Okay. You don't need to print the density. We can just look that up. And then I think the data tables are, yeah, you should print the data tables because those aren't on here. If you don't want to print the data tables and you want to just keep it in your notebook, that's fine. You can make your own data tables. But in this lab, since we are just recording a bunch of data, it's easier if you just have the data table. I think it says on here for pre-lab preparation, construct tables in your notebook. So you don't have to do that if you print out the table. Just bring that. You don't have to do both. All right, the biggest part of the lab tomorrow is pipette skills. I don't know if I could turn this thing around. I don't think I can rotate it in this browser. That's okay. We'll go through it tomorrow. Who here has used a volumetric pipette before? A few people? With the finger thing and the bulb? Okay, good. You'll have a head start. So the toughest part about the lab tomorrow is the precision that you need to have with your actual physical lab skills of working this thing with your hands. It can be really, really frustrating until you get it. So make sure you don't drink too much coffee. Don't be jittery when you come in tomorrow. Try to just take some deep breaths and be ready for some very precise hand work. That's gonna be the most difficult part. We're just using water and isopropanol, so there's no particular hazards you need to worry about for the lab tomorrow. But what I would ask you to do, not there, here, nope, not there, here, okay. Where'd that procedure go? There it is. What I would ask you to do is, please, please, please read through the entire lab and think about what you're actually trying to measure tomorrow. This is a lab that it's pretty easy to do, and you follow the directions and you do the thing. But because I think it's kind of easy and there's nothing really complicated about it, it's in the past I've seen just crazy numbers coming out. And I think it's because people are sort of just following the procedure without thinking about what you're actually doing. So the point of the lab is the question that's in the title. Are the volumes of pure substances additive? That means when you put 5 milliliters of water and 5 milliliters of alcohol together, do you get 10 milliliters? We're going to test that out. So what do you think? Are they additive or not? You take 5 milliliters of water, 5 milliliters of alcohol? Maybe? You think so? Okay. Well, we're going to test it out and see. So how do you test that? Any ideas? How would you figure that out? You want to know exactly how much you get when you mix those things together. The volumes are added.
Measure 5 milliliters of each formulated together.
Yeah, you measure them out and form them together, but the problem is, how do you measure that final volume with the same precision as the pipettes? Because if you just put them together in, let's say, a graduated cylinder isn't as precise as a volumetric pipette. So it might not work out as well. So what we do instead is we use a density. We take a known amount of each one, mix them together, and then measure the density and calculate the volume from the density and the mass. So it sounds, I know it's a little confusing. You'll see when you read through it, but that's what I'm asking you tonight. If you get a chance, please read through this. Think about what you're going to be writing in those tables and how measuring those things is actually going to be able to allow you to figure out whether or not the volume is additive. In the there's a first part of the lab, which is just kind of getting used to using glassware. So you're going to measure water using a Erlenmeyer flask, a graduated cylinder, and a volumetric pipette. And then you're going to check that, and you're going to try it a couple times and just see what works. You could probably guess that the point of this exercise is that you get more precise as you go from flask to graduated cylinder to volumetric pipette. But that is really, really technique-based. And the volumetric pipette is the hardest one to use. So make sure that you're really patient and that you're taking the time to do the volumetric pipetting properly. I would also, just a little bit of a warning with this lab, I don't expect any issues in this class, but in terms of academic dishonesty, cheating type stuff, falsifying lab data is considered the exact same as like cheating on a test. It's the same level of academic dishonesty. So if you're ever tempted to be like, well, I know this is supposed to be 5, even though we got 4, so I'm just going to write down 5, don't do that. It's not what the lab is about. You're not getting graded on your perfect lab technique. You're being graded on how well you write about this stuff. There's no need to do that, falsify data. Same thing with, let's see, I've seen it in that situation. I've also seen it where people really want to be done with lab. And so they think like, okay, well, I know what this rest of this is supposed to be. So I'm just we'll do one trial and then we'll just write a couple more for the other trials and then we'll be done. Don't do that. It's not good science. But you're not gonna do that. Not worried about it. Okay, well, I will see you tomorrow. Please start in with mastering chemistry if you can get signed up. If you're having trouble or you can't get it for some reason, you know it's going to be a while, let me know so I can help you with that. Otherwise, yeah, happy problem solving. See you tomorrow. Yes. Yes. Except this, the data can go directly.
There's no real lab manual. The lab manual are the sheets that you have there. The lab notebook is free, you just put in the data. Get the books for you. You can use whatever, you can use a normal notebook, use that notebook, doesn't matter, but if you want like the carbon copy, it's $10.
See ya, have a nice day.
So Joe, do we have enough to do bachelor chemistry 1